Edeling from CWI in Amsterdam, and he's going to be talking to us today about very large parameter problems. So, Wouter, if you're there, I will pass over to you.
You can see my screen and hear me, I suppose.
Yes, we can.
Okay, good. Let me just make this large. Yes. Okay, so thank you again for having me. I'm going to be talking about, again, a forward UQ problem. So we're not calibrating, we're just propagating uncertainty forward through the model. And if you were present at Tuesday's talk, I was talking about stochastic collocation and an adaptive version of it. And I've mentioned this before, but just a short recap. That if you do these kinds of methods, you're relying on one-dimensional quadrature nodes, which are extended to higher dimensions via tensor products. And it's this tensor product that can become potentially very expensive in number of simulations. And if you do an adaptive version of that, you are making your sampling plan in an iterative fashion. Right? You're starting with a single sample and you're building it up in directions which turn out to be important. Right? And that way you get an anisotropic sampling plan that refines the important inputs. It's still based on tensor products though, right? So you don't get around that. It's still a tensor product based approach. And yeah, if you then visualize the refinement, you get a similar plot like this, right? Iteration number and inputs on the vertical, and the colors denotes which combination of inputs got refined at what time. Now this has a potential downside, and that is, I'm saying potential, it doesn't have to be a downside, but you have this big problem and you're breaking it up in small pieces. But with this method, you're breaking it up in a lot of small pieces. I'm just showing you 70 iterations. I think for the COVID sim work, we needed like 130 or something. And if you look at the number of new samples that you compute at each iteration, it's rather low. Sometimes you might get 40 or something, but on average, it's around 10 new evaluations. And this, well, if your code is very, very expensive, then this might not be a downside because you're still utilizing a large part of your machine in that way. But let's say if you do get like a large allocation on a supercomputer, and maybe you get it for a short amount of time, then this might not be the right way to go. Right, and also in the case of COVID sim, it's an HPC application, but as I mentioned before, it's not a massive one. Right, and I'm chopping it up in even smaller pieces here, so it might be nicer to just take a single ensemble and just fill up the machine and run that. Right, and another potential downside is if I have 100 iterations, I might run into queue times. Right, if the machine is very busy, there might be a long queue time, so you would have to wait a bit before every iteration or before every ensemble actually gets submitted. Now, I'm going to talk today about something called active subspaces, which doesn't have this problem. And if you look at stochastic collocation, again, your coordinate axis will be aligned with your input axis. Right? And here I'm calling the input x. And the factorial, right? Your input axis are your coordinate axis. But it is quite likely that if you're able to visualize the variation of your function, for instance, by contour lines in this two-dimensional example, the direction along which this function will vary the most, it's probably not going to be aligned with x1 and x2. Right? It might be something else. And in fact, in this example, if you look at this line over here, it contains all variation, and right, the function is constant along this direction. And so the general idea of the active subspace method is trying to find these directions. Right? You're rotating your coordinate system, and then you're dropping the directions along which the function doesn't vary much. And in this way, you hope to get a lower dimensional coordinate system along which your function will vary the most on average. Now, in order to do that, you want to find the active variables, which are called y here. And by the way, if you want to read about active subspaces, it was developed by Paul Constantine back in 2014. And the goal here is basically to find this matrix U1 here. Right, this dimension D times, or capital D times small d, where capital D is the number of inputs, and small d is hopefully a lot less, right, in the number of active variables. And so it's a linear projection. And if you're able to find that, then the next step would be to make like a circuit model of your code. I'm calling it G here, but then in the reduced input domain. And so those are the two things. And then of course the questions are, what is U1 and what is going to be G? Now for the first one, finding U1, again, remember we want to find directions of large variability. And so it might be a good idea to involve the gradient of the code somehow. And what active subspaces do is they construct this matrix here, the C matrix. Right? It is like, I would say, like an uncentered covariance matrix. Right? There is no mean, but there's still a covariance structure that involves your code gradient. Right? And it is weighted by P of X, where this is the input distribution of your inputs. Again, it's something we have to assume, but if we have an assumption on the input distributions, you could compute this weighted matrix. If you don't have a lot of inputs, you could maybe do some quadrature rule. If you have a lot of inputs, you could maybe compute this with Monte Carlo. But in any case, you can see that because of this transpose here, it's a symmetric matrix. So we'll have an eigenvalue decomposition in which the eigenvectors are orthogonal to each other, or they have orthogonal columns, I would say. And then you can look at the decay of eigenvalues. So you rank your eigenvalues from largest to the smallest. And what I'm doing here is I'm pooling all the large ones in lambda 1 and all the small ones in lambda 2. And you're hoping, of course, that there's a big gap between lambda 1 and lambda 2. And if you do that, it's kind of like a PCA, except using the gradients of the output. And so if lambda 1 contains my small d large eigenvalues, then U1 are the eigenvectors that point in the direction of greatest variability, right, on average, because I'm averaging over the input distribution. So with this, you have defined your active subspace. Right, again, this linear projection. And now we know that U1 are the dominant eigenvectors of this C matrix. And in the same vein, you could define inactive variables, right? It's just a U2 transpose times X. And then the last thing you have to do here is make a circuit in the reduced space. And this could, in principle, be anything, although typically I think a circuit that regresses would be better than an interpolation-based circuit. So maybe you could do Kriging, or you could fit the Gaussian process or something like that. Now the issue here with C, it depends, of course, on the gradients. So you need to be able to compute that. And this is not always easy. If you can do it, though, I think it's a very good method to use, and probably better than the method that I'm going to describe. But if you have a lot of inputs, maybe this is not feasible, or maybe there's some weird bifurcation behavior, or there might be all kinds of problems why it might be hard to compute your gradients. And so there are alternatives that use like active subspace-ish ideas, but without having gradient information. One of them is based on Gaussian processes. That's done by Serge Guyas and his students. And the other one is based on neural networks. And they were introduced by Tripathi and Bilionis, I think from Penn State in the US. And that's the one I will focus at. It is, of course, in a sense similar to let's say the classical active subspace, in the sense that I'm still looking for active variables, which are a linear projection of the inputs. I still have a vector, not the same one now. So that's why I've called this one W instead of U. It has the same dimension as U1, and like U1, the columns are still orthogonal, or orthonormal even. And I'm still looking to make a surrogate model in the Y space. Now it is different because W1 is no longer the set of D dominant eigenvectors. In this case, it's parameterized by Gram-Schmidt process. So I'm guessing most, if not all of you, are familiar. But let's say you have a set of vectors Q. They're independent, but they're not orthogonal to each other. And then you can apply Gram-Schmidt in order to get these W's, which are orthogonal. And in these Q's, they are the columns of this Q matrix. And my orthogonalized vectors W will be the columns of my W1 matrix. And this then becomes the weight matrix of in my case, a simple feed-forward neural network, but with linear activation. And if you do linear activation, you will just get the same active subspace projection back. If you see there's a middle expression over here, that's the standard representation of a hidden layer of a neural network. You have the output of the previous layer, which in my case is the input layer. So it's X. You pre-multiply with your neural network weights, and then you apply some activation. And if it's linear, I just get the active subspace back. And this means that you can plug this in as the first hidden layer of a neural network. If this is my input layer, this is my reduced input space, Y. And then the columns of W1 are the weights on these lines connecting the inputs to each neuron in the first layer. Now, I'm using a couple standard things here to train it. I'm using the squared loss. I'm going to minimize the code outputs F. So again, not the gradients of F, but I'm using only the code outputs and the surrogate prediction. This is a standard neural network update step. That you minimize your weights based on the gradient of the loss. However, here in the second layer, which I'm calling the deep active subspace layer, it's different, right? Because W1 is not random, right? It's parameterized. It has to be orthonormal. So I have to optimize with respect to Q first. And so this will be my update step, where alpha is the learning rate that you can estimate somehow. It's not really important here. But then if I look at this gradient here, right, L is a scalar, Q is just a matrix, so this becomes a matrix. If I look at a single entry of the matrix, I get this expression, this one. And partial L, partial W1, that's just the output of standard backpropagation, right, the gradient of the loss. But I also need this guy here. And right, so you can see that what I need to compute extra compared to a standard neural network are the derivatives of the Gram-Schmidt vectors. Right, this is not exactly the same, but if I have this partial derivative of W1 with respect to Qj, I can compute these terms here. Right, it's just a matter of reshuffling some columns. So what I need to do is compute this matrix, this derivative of the orthogonalized vectors with respect to the original non-orthogonal vectors. But because each vector W is a function of all Q vectors up to I, so Wi is a function of Q1 to Qi, this becomes a pretty complicated expression. That you could plug this into Maple or some other computer algebra system and just compute it brute force, and you'll see that you get a massive expression. And so this is why the original authors of the first article, they used automatic differentiation. But we did something different, and we used matrix calculus. So even if the brute force expansion of this gradient is very complicated, you can find a recurrent relationship that is pretty simple and pretty easy to implement. So you can exactly compute this analytically, and this is what we used. Now, I don't know which one of the two is better yet. It's still work in progress. I kind of like the analytical expression because it you get a bit more insight, I think. And it might be useful outside the context of active subspaces. And so that's why I've placed it in a separate GitHub repository. But anyway.
We've got about 2 minutes left.
All right, I'll speed up. So once you've got that in place, then this bit is done. And then the surrogate is just the feed-forward network, right? The network after the first layer. Right, and for this, I don't need adaptive sampling. Right? I just need the training database, which I can generate with Monte Carlo. Now, I will apply this to an HIV model, which is the same one that I showed in the tutorial yesterday, so I won't go into it in detail. 7 ODEs coupled, 27 inputs. I'm assuming uniform distributions, which I first normalized to lie between -1 and 1. And then I train my network on that. And the nice thing about this model is that I have a reference solution. This model has been the classical active subspace, the one with derivatives, has already been applied here, so I can compare. And so this is the eigenvalue comparison between two. This is the reference case. This is what I get from the network. And I don't have to compute this, but once I train my network, I can compute the gradient if I want to in a post-processing step, so I can compare the eigenvalues. And you can see that in the case of the neural network, in this case, I've selected d is equal to 1. Then all the other eigenvalues are exactly 0. But if you look at the reference case, you can see that for d is equal to 1, you get an eigenvalue of roughly 5 or between 5 and 10. And the next one is 2 orders of magnitude lower. So this is an indication that you do have an active subspace. And I'll skip this. Now maybe I'll talk about this briefly still. So this is the heat map of this matrix for the reference case, the deep active subspace, but also for a standard neural network. Right? I don't have to apply this dimension reduction. I could do the same thing for a standard neural network. But then you can ask yourself, so what's the point of having this active subspace layer to begin with? And to do that, I've compared the performance of a standard neural network versus a deep active subspace neural network using standard training test split, right? So you take your training data, but you use only part of it to train it, and you test your performance on the remaining data. Right? And you can see the performance for the neural network, which is in blue. It does better on the training data, but then when it's time to test it, it's overfitted, so you get a jump in error. And in the case of deep active subspace, the performance is very consistent between training and test sets. And the error bars that you see here are constructed from replica neural networks. So I didn't train a single neural network because these have some stochastic component in them. So I did it 100 times to compute these confidence intervals. I will skip that. And this is the visualization of the active subspace. So blue is the code, which is 27 dimensional, but I just plotted along this one dimension. And then the orange line is the 1D surrogate approximation. So you can see that even though you have 27 inputs, if you're able to find these directions, it's really just one dimensional at a given time. At a later time, it's still pretty much one dimensional, although there is a little bit of variation over here. And you can do the same with CoverSim. So that was the HIV model. This time we applied it to CoverSim with 51 inputs. Again, same procedure, standard Monte Carlo sampling. Submitted the jobs to the Eagle supercomputer. And look for the decay in eigenvalues. And this time I had to choose 2. So there's roughly a 2-dimensional active subspace. And I can again compare the response surface in this 2-dimensional space. So this is my 2-dimensional surrogate. That's the actual data, the 51-dimensional data plotted on this 2-dimensional space, and you can see it matches up pretty well, despite having some noise in the data here. And with that, I'll just leave the conclusions up. And this is now preprint, so it's on a review. And if you want to reproduce the results, all the code and all the data is available here. So thank you.
Much, Wouter. So we're into the break period now. So maybe if there's just a quick question, if anyone has a quick question on the floor, or are there any questions? Quick questions. In which case we might, because we're running a bit over time, so we might just we can always come back to any further questions people have in the discussion session. So thank you very much.